Hi, my name's Chuck. I'm a programmer and a math tutor, and today we're going to talk about conditional probability and one of the classic problems in this area. So here's me, and let's say I have this friend named Alex, and I'm talking to Alex one day, and the subject of kids comes up, and I ask, hey, remember our old friend Bill? Didn't he have a couple of kids or something? And Alex says, yeah, he has two kids, actually, one girl, and I don't know about his other one. And what about our other old friend Dave? Uh, he also had a second kid recently, and I don't know about the newborn, but his older kid is a girl. So let's look at these two statements here. Bill's got two kids, at least one of which is a girl, and Dave has two kids, the older of which is a girl. And that brings up the question, what's the probability that Bill has two girls, and what is the probability that Dave has two girls? Are they the same? Let's find out here. So to dive into this problem, what we need is called conditional probability. So often we want to find the probability that two things both happen. For example, let's take a look at the probability of rolling double sixes on a pair of regular dice. So the first got to be a 6 and the second also has to be a 6, and the two dice happen to be independent of each other, meaning the probability of getting a 6 on the second die is not affected by what happens on the first. Intuitively that makes sense, right? They don't affect each other, and each probability is going to be 1/6 regardless. By the way, if you ever make it out to Las Vegas, which you should, and play roulette, which you probably shouldn't, don't be fooled by these electronic signs next to some of the tables that tell you what the last 10 or 15 or so spins landed on. Because similar to the dice rolls, you don't need me to tell you that these spins are independent of each other, and the fact that we've hit red 6 straight times or 19 7 straight times says nothing about what's going to happen next. Red isn't hot, black isn't due, and it's probably not going to land on 19 on the next spin. The sign is just to make you think those thoughts and to get those dollar signs in your eyes and to get you to the table to give the house your money. You still have a 1 out of 38 chance of hitting 19 on the next spin and a 9 out of 19 chance of hitting red. It's not going to change. Snapping back to reality, we can think of the dice like this. 1/6 of the time we get a 6 on the first die. And out of those trials, 1/6 of those will result in a 6 on the second die. So 1/6 of 1/6 is 1 out of 36. And that gives us kind of a geometric representation of this problem as well, which brings us to the mathematical definition of independent events. So when we calculate the probability of two or more independent events all happening, the overall probability is just the product of the individual probabilities. In other words, the probability of rolling a double 6 is the probability of getting a 6 on the first die times the probability of getting a 6 on the second die, or 1 out of 36. All right, so now let's go back to half of the problem at hand here. We're going to assume for the purposes of this problem that every kid's either a boy or a girl with 50% probability, and the sex of each kid is independent of that of their siblings. In other words, each kid is an independent coin flip when it comes to their sex, and so we're going to start with Dave. His older kid's a girl. What's the probability that his younger kid's also a girl? Well, since the sexes of his kids are independent of each other, we know it's 50%, and thus the probability that Dave has two girls is also 50%. So I bet you agree with me so far, but we're going to come back to this later too. But what happens when two events are dependent on each other? In other words, when the occurrence of one affects the probability of the other one. For example, what's the probability that it's cold outside? Well, I'm recording this from my basement indoors and away from windows, so I have nothing to go on here other than the fact that it's December in Maryland. So the probability is probably pretty high, like 60 or 70%. And if I were to go upstairs and look out the window, though, my answer would change. It'd be lower if it were sunny, and if it were cloudy or raining, it'd probably be a little higher. So how do non-independent events affect each other? Well, let's draw the grid representing two events. One that it's sunny on the left side there on the left axis, and one that it's cold outside on the top axis there. Actually, it doesn't really get hot in Maryland in the winter, so we're just going to say comfortable instead. But from my basement, I don't know if it's sunny or not, so our universe of possibilities is this entire diagram. It could be sunny and cold, it could be sunny and not cold, it could be cold and not sunny, it could be neither cold nor sunny. So let's arbitrarily assign some probabilities to this grid. It's usually sunny here, but since it's December, whether it's cold or moderately comfortable is basically a coin flip. So we'll say there's a 30% chance that it's sunny and cold, 30% that it's sunny and not cold, and that leaves us with like 40%. So we're going to say there's a 38% chance of clouds and cold, and like 2% clouds and not cold, because that doesn't really happen very much. The probability that it's cold outside is just the total probability of this cold column, which is 68%. So from my basement, I tell you there's a 68% chance that it's cold outside. Similarly, the probability that it's sunny is 60%. But what's going to happen if I go upstairs and look out the window? So let's say I go upstairs, look out the window, and see it's sunny. And now we know some possibilities can be eliminated, specifically anyone where it's not sunny. And now our universe of possibilities is just this sunny row up top. Now, the probability that it's cold is the probability of this box where it's both sunny and cold, divided by the total probability of the sunny row, which brings us to the definition of a conditional probability. The probability of A, given that B has already occurred, is the probability that both A and B occur, divided by the probability of B occurring. In our case, the probability that it's cold, given that it's sunny, is the probability that it's cold and sunny, divided by the probability that it is sunny, or 30% divided by 60%, or 50%. Similarly, if it's cloudy outside, the probability of being cold is the probability of being cold and cloudy, 38%, divided by the probability of being cloudy, or 40%. And that's 38 divided by 40, or 95%. Let's go back to that definition for a second. The probability of A given that B has occurred is the probability of A and B divided by the probability of B. So what happens if A and B are independent? Well, we had that previous definition where the probability of A and B both occurring is equal to the products of their individual probabilities, right? So we can substitute this. We can substitute the probability of A times the probability of B for the probability of A and B. And suddenly the probability of B cancels out, and we're just left with the probability of A. In other words, the fact that B has occurred does not affect the probability of A. So we're kind of back to our original probability here. So now let's go back to our friends Bill and Dave. Now for both of them, we can make this grid of probabilities for their older and younger kids. And we know, since the sex of each kid is independent of the others, the probability of boy then a boy, or a boy then a girl, or a girl then a boy, then a girl and another girl are all 50% times 50%, or 25%. So let's first look at Dave again. As a reminder, his older kid's a girl, so we can eliminate the scenarios where his older kid is a boy. And we can say now that given his older kid is a girl, the probability that his younger kid is also a girl is the probability that they're both girls divided by the probability that the older one is a girl. 25% divided by 50%, or 50%. Now, this is not surprising because we kind of already figured this out a little earlier, right? So the probability that Dave has two girls is 50%, or if you want, 1/2. Now let's take a look at Bill, who, as a reminder, has two kids, at least one of which is a girl. You might say the probability that he has two girls is also 1/2, at least one girl, and the probability that the other kid's a girl is still 1/2, right? Let's start with the visual first. We're going to start with the same grid, but instead of keeping the possibilities where the older kid is a girl, as we did with Dave, we're going to keep the ones where at least one is a girl, meaning we're actually only getting rid of this one possibility where both kids are boys. And now you're hopefully starting to see how these two scenarios are actually different. The probability of having two girls, given that at least one is a girl, is the probability of having two girls and at least one girl, which is kind of redundant, but whatever, divided by the probability of having at least one girl. So from the visual, you can see that this is actually 25% divided by 75%, or 1/3. So if Bill has two kids, at least one of which is a girl, the probability of him having two girls is actually only 1/3. But why isn't it 50-50, you might ask? Well, it would be 50-50 or 1/2 if the possibility of having two girls and the possibility of having one boy and one girl were equally likely, but it turns out they're not. Having two girls is a 25% chance, and having one boy and one girl is a 50% chance, meaning having one boy and one girl is twice as likely as having two girls. And this is actually borne out in the fact that Bill's probability of having two girls is 1/3, and the probability of having a boy and a girl is 2/3. Now, if you still don't quite believe me, I've coded up a simulation of this scenario, which I'm going to link in the description of the video below. I'm going to kick it off here, and it's going to simulate, let's say, like 5,000 trials of having two kids, and we're going to see what happens. And you can see pretty quickly, actually, the numbers start to settle around the answers that we got. When you have the older kid being a girl, right around half the trials end up being two girls as well. And then when there's at least one girl, right around 1/3 of the trials also end up being two girls. And when we let this finish up, should take another few seconds here. There we go. You can see that right around 3/4 of the trials, 3,786, 3,750 would be exactly 3/4. But right around 3/4 of the trials have at least one girl, and 2,481, right around 1/2, have the older child being a girl. And as we'd expect, of the trials where we have at least one girl, about 1/3 of them, 1,216, have two girls as well. And if you still feel a little skeptical, I'm going to leave you with one last scenario, actually. Let's say we have two coins, one of which is fair, and the other which has two heads. If I randomly pick one and then flip it 10 times and get all heads, what's the probability that I pick the rigged coin? Just because I picked randomly at the start doesn't mean it's 1/2 either. And I'll bet you believe that it's more likely that I pick the rigged coin and flip 10 heads in a row than I just flip 10 heads in a row with the fair coin. But we're going to take a look at this one on the next video. And hopefully I'm going to continue making these. I don't plan on having any real structure other than sharing an interesting problem or a concept each time, but I'm open to suggestions. And regardless, give me a like and subscribe, and thanks for watching.